Hello, this is Dr. Oz. In this problem, I will do another example of nonlinear programming called facility location problem, which is a very important problem for many companies to choose what is the best location for their facility. All right, so in this example, I have LaRosa company, and they have fabrication, they have paint, they have sub-assembly 1, they have sub-assembly 2, and the assembly departments or locations. And each of these locations are given in terms of the X and Y coordinates. X coordinate versus Y coordinate. All right, so X coordinate of fabrication is 1, Y is 4, paint 1, 2, sub 1, 2.5, and this can be meters, inches, yards, whatever, miles, depending on the problem. 3 and 5. Assembly is 4 and 4. So these are my given parameters for this problem. So now I would like to find the best location for my tools, let's say. I will create my model. This could be find the best location for your warehouse. It could be tools. It could be another department. It could be ER room in hospital. So this kind of problems have a wide variety of applications. Okay, so I'm gonna calculate. That location. That's my goal, right? So let me just briefly talk about intuition before I dive into this. So if I go back to my intuition, so what's going on here, right? Let's talk about that. So here again we have machine shop LaRosa and trying to locate tool bin in this case, and so that to minimize the distance, increase the efficiencies. So now I can define my decision variables in this problem as X and Y, which is the horizontal location, and this is my vertical location. Okay. So if you think about this in an area like this, these are my departments, and I'm trying to locate my toolbox. Let's say, should I put it here, 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 obviously somewhere in the middle, right? I'm trying to figure out this location, best location that will minimize the total distance from all these departments. To be able to minimize something, you got to measure it, and we measure these kind of locations based on Euclidean, which is straight line distance. And if you remember your geometry class from high school, my location X coordinate for decision variable minus, let's say for 1, 4, X is 1, 4 is Y, X minus 1 square plus Y minus 4 square will give me the Euclidean distance. Y, if you remember geometry again, is a 90-degree. So let's say if this location is your 1, 4 coordinate, let's say, I'm trying to figure out this distance xy from 1, 4. This is their distance, right? So you are trying to figure out this distance. To be able to do that, you can do, this is x minus 1, the distance here, and the distance over here is, let's say, when I say x and y, they can interchangeably, it can be y minus 4 So if I want to find this distance again, x1 is 1 square plus y minus 4 square root of that. So that's why this is coming from basically triangle, which is straight line between those two locations. So this is the tool-bill location that I'm trying to figure out. We minimize distance. Okay, so I gave you the background information. So let's see whether we can solve this problem. Again, I'll start with my problem with my objective function. So the objective here is minimize total distance. All right, I will calculate that right here. And I need to calculate this value based on my decision variables. So my first decision variable is x coordinate, and another one is y coordinate. These are going to be my yellow cells. Perfect. So there is no constraint here, really. That's why I will leave the constraint part blank. So instead of calculating everything here, what I'm going to do is make my life a little bit easier and calculate those values over here. Distance. So let's start with a random point so that things will be easier to calculate. So let's say if my random point is 1 and 1, the distance between fabrication and that toolkit is going to be square root of, in parentheses, 1 minus 1 square plus, in parentheses, 4 minus 1 square, and close my parentheses, square root. So the square root of this will be obviously 3. All right, so I want to make similar calculations for other departments too. So I need to lock my E and F6, F4, and F4. Now I can drag it down. So these are my Euclidean distances. So I would like to minimize basically the sum of these Euclidean distances. All right. So data, solver, again, if you don't have solver, file, options, add-ins, analysis toolpack, click on go, and make sure you check solver add-in, and then it will take a minute. So solver, my objective value, click on this icon, is the green cell, enter. This is a maximization or minimization problem. So it's minimum total distance. So I will click min, and decision variables are these values, and I would like to add my constraints, which I don't have any, so I will leave it blank. And I want to make sure that I can get negative values. That's okay. So uncheck this. I'm using nonlinear programming because my objective is square terms. Basically, it's not a linear equation. It's a quadratic equation. Excuse me. And when I solve this problem, I will get the best solution as 8.3 distance, let's say 2.3 yards or miles or whatever, right? Depending on the problem. And the best coordinate for my toolbox is 2.2 and 3.3. All right. And that is the best locations, which will end up in, you say 2.2 and 3.3. Okay. So that will give me the best solution. That's it for this video. Next video, I would like to talk about another nonlinear programming application, which is Markowitz's portfolio model. Until next video, enjoy business analytics.